All right, well, I'm excited to say that we have reached the end of Module 4. This is the last video. I'm just going to do a quick recap and overview capacitors and inductors and kind of compare and contrast them. We looked at them individually, and now I just want to look at them side by side and kind of give a brief overview of what each of them are and what they do. And so this is the two pictures that I use to describe the physical realization of capacitors and inductors. The one, obviously the capacitor on the left and the inductor on the right. So I'm going to go ahead and move on to this little slide right here where I'm going to pull out my highlighter and just make some notes. So of course the capacitor, this is the symbol for the capacitor on the left. Let me grab my highlighter and just highlight some notes. The capacitor is two conductors that are separated by an insulator. Okay, and so of course I have my first conductor on the left and my second conductor on the right. In terms of my symbol, it's pretty self-explanatory. And these capacitors store their energy in the form of an electric field. We know that when the capacitor has voltage across it, then it's storing energy, 1/2 CV squared. We also know, we learned that the capacitance itself depends on the area of the plates, the permittivity of the dielectric, and the distance between the plates. Okay, we know that the capacitor, because it is two conductors separated by a physical insulator, at DC, it is an open circuit. It does not allow current to flow at DC. It is an open circuit, okay? That's the important piece for the capacitor. And then voltage cannot change instantaneously across the capacitor, right? We know that this is because our equation for the current through the capacitor is equal to C dVc dt, and in order for the voltage to change instantaneously, dt would have to tend towards 0, which means my current would have to go to infinity, which is physically impossible. Okay, so that does not occur. All right, and then in terms of inductors, let's pull out a different color highlighter. We have a conductor or some kind of wire that's wound around a magnetic core. Of course, in both cases, the core itself can be it can be air. It doesn't necessarily need to be a good magnetic material in order for us to have an inductor. It needs to be a good magnetic material in order for us to have a good inductor, or a good dielectric material in order for us to have a good capacitor. But even if we don't have those, the dielectric or the magnetic core, we still have an inductor if we wind it around air, or we still have a capacitor if we have two conductors separated by air, okay? The inductor stores its energy in magnetic fields, okay? And we know that the energy stored is 1/2 times L times I squared. And so as we get current flowing in our inductor will be storing energy in the form of a magnetic field. Because the inductor is just a wire, it is a short circuit at DC. Nothing interesting happens at DC. It just behaves like a short circuit. And finally, current through an inductor cannot change instantaneously, right? And that is because our voltage is L DIL dt, and dt would have to go to 0 in order for our current to change instantaneously. And that would result in infinite voltage, which we know is not realizable in real life, so that is not practical. And that is about it. I have compared and contrasted the capacitors and the inductors. I think this is a good review slide. I guess the last thing here is that we discussed that the inductance depends on the number of turns. It depends on the total length of the wire. It depends on the diameter of the turns, and it depends on the permittivity of the magnetic material, or the permeability of the magnetic material, which is mu. Okay, that wraps up Module 4. We are officially done with Module 4, and I am excited to move on to the final module of this class, which is Module 5. Look forward to starting those lectures very soon. So I'm going to go ahead and wrap this up, and congratulations on making it through this module. If you made it through this module, I'd say that you've gotten through the most difficult part of the class, and we're just about done with all the hard stuff, okay? So signing off here.